Okay, now question 4 of the exam 1 review. We're given a context. We've got helium gas, told it's a monatomic gas. It means single helium atom. It's a noble gas. It has a molar mass of 4 grams per mole. What is the RMS speed of a helium molecule at 30 degrees Celsius? So, sort of, if we think about the context of the question is definitely referring to RMS speeds. That's the main concept of this question. And it's asking us for the RMS speed so that we won't have to rearrange the equation for the RMS speed. So the RMS speed, if you look at your equation sheet, is given as 3 or, this is the gas constant, 3 or T over the molar mass. We can also describe the RMS speed in terms of the mass of a single molecule, doing 3 kBt using Boltzmann's constant. But these are typically not known, well, not given typically. It's more common to know the molar mass than it is to know the mass of a single helium atom. But we could get to the single helium atom using the molar mass and Avogadro's number, but that's the connection between the Boltzmann constant and the gas constant. So I tend to focus on the equation here on the left as using the gas constant and using the molar mass. Now we want the RMS speed in meters per second. These are the SI units for speed, so distance or displacement over time. So that means that our R, T and molar mass need to be in SI units. And that's sort of the difficulty of this question, not so much in knowing what the concept is or the equation, it's about unit conversions. So the key thing here is the temperature. You want the temperature in Kelvin. So that's going to be our 270 Kelvin, 273 Kelvin plus 30 and give us our 303 Kelvin. So they're making sure you're converting your temperature to the correct SI temperature. And what's kind of tricky here is the molar mass. So it's very common to give molar masses in grams per mole. It's the most common unit for molar mass, but the gram is not an SI unit for mass. So some students will get caught up here and not correctly convert the molar mass. So the molar mass must be in kilograms per mole. So that means it's 0.004 kgs per mole. And once you have those two conversions, you should be good to go. The gas constant should be again in SI units, and that should be your 8.31 value, joules per mole Kelvin. I know some of the chemists like to use different values of the gas constant, but I only recommend using the SI quantity, so 8.31 joules per mole Kelvin. So then we can figure out our RMS speed. So 3 times 8.31 joule per mole Kelvin times the 303 Kelvin. So those Kelvins will cancel. And all divided by the molar mass, which is the 0.004 kgs per mole. So the moles will also cancel in this case. And then if you're wondering where does the meter per second come from, it's hidden inside the joule. So the joule is a unit of energy, which we can go back to force. I'm thinking joule's unit of energy, so we think about work equals force times distance. So a joule is the same as a newton times a meter, and inside a newton is a meter is a mass times acceleration. So you can go through your unit knots if you want, but you need the cancellation here is that because inside the joule there's a kilogram, the molar mass must be in kilograms. So this gives us an answer of choice E, 1370 choice E is correct. Okay, I should do a little bit of sense making and do a couple of extra things here just for additional sort of note taking. So the RMS speed of N2 at room temperature is a good thing to know. So since most of the air is made up of nitrogen, so this is a diatomic molecule with 28 grams per mole. If you work out your calculations at room temperature, it would be 293 Kelvin, and this is 28 grams per mole, so 0.028 kilograms. You get about 510 meters per second. So your RMS speeds for typical gases at room temperature are quite high, many hundreds of meters per second. So what we're looking at is a much smaller gas molecule. So the RMS speed is inversely proportional to mass. So we should expect, again, given the temperature, not knowing the temperature yet, but a smaller molecule at the same temp would definitely move at a significantly higher speed. So not only are we looking at a smaller molecule, a significantly smaller molecule than nitrogen, we're also looking at a higher temperature than room temperature. So we should expect, in both situations here, we should be expecting a speed much greater than certainly greater than the speed of nitrogen at room temp. So the only reasonable answers are D and E. So it's a way of you, in a sense, doing some sense making before you make the choice. You could say, well, it definitely can't be, I expect it to be this, definitely above 500. And the other thing, just to sort of know some of the distractors here, the 43.5 meters per second, that comes from using 4 grams per mole, I believe, with the correct temperature conversion. Yes, so with the correct temperature conversion but not converting the mass correctly, you would have gotten A. And C would be using the correct correct molar mass, but using 30 degrees instead of 303 Kelvin. So yeah, again, it's just a question that certainly highly emphasizes the importance of units. And it should give you choice E as the correct answer.